To maintain their basic functions, healthy tubular epithelial cells burn through massive amounts of ATP. ATP, or adenosine triphosphate, is the primary molecule that stores and transfers energy within cells. These cells shoulder a unique dual responsibility. They provide structural support for overall blood filtration, while simultaneously performing continuous, heavy-duty reabsorption and secretion of fluid and electrolytes. Because of this extreme energy demand, a localized ATP failure directly wrecks the cell's transport machinery and its ability to control electrolytes. The proximal tubule requires the highest rate of active transport of any segment in the nephron. This workload makes it the most inherently fragile tissue in the entire organ. The kidney's own structural efficiency creates its greatest vulnerability. If the energy supply to these transport-heavy cells is even briefly interrupted, the entire system faces catastrophic failure. This diagram maps acute tubular injury as a 10-step pathophysiological cascade. The primary and most common trigger is ischemia, where localized blood flow is abruptly cut off, starving the tissue of oxygen. Other systemic triggers like severe sepsis, circulatory shock, and circulating nephrotoxins also initiate the exact same cascade by disrupting the cellular energy balance. Endogenous proteins can also act as severe toxins in this pathway. In rhabdomyolysis, muscle breakdown releases large amounts of myoglobin into the blood, which directly poisons the tubular cells. Regardless of the exact trigger, the common denominator is a sudden drop in available energy. The cell is pushed past its structural breaking point, and the cascade begins. Following the initial ischemic insult, step 2 begins as intracellular ATP levels plummet rapidly. As this diagram illustrates in step 3, the immediate casualty of this energy crisis is the failure of the sodium-potassium ATPase pump. This specific pump is required to maintain the electrical and chemical gradients of the tubular cells. Without it, cellular polarity is completely destroyed. An abrupt osmotic shift follows. The active reabsorption machinery collapses. Water rushes into the intracellular space unchecked, and the cells begin to rapidly swell. Swollen and deformed, the cell loses its physical grip and detaches from the underlying basement membrane. The loss of ATP results in the physical dismantling of the cell's structural anchors. The tissue is tearing itself apart. Step 4 occurs inside the newly detached cell. Ion regulation breaks down completely, causing a massive influx of calcium from the extracellular fluid. This sudden spike in intracellular calcium directly shreds the cellular cytoskeleton. The calcium spike dissolves the delicate brush border at the top of the cell and severely exacerbates ongoing damage to the mitochondria. Concurrently, in step 5, reactive oxygen species begin to flood the local environment. Reactive oxygen species, or ROS, are highly unstable oxygen-containing molecules that easily react with and damage other cellular structures. These destructive free radicals originate from ischemia-reperfusion injury, circulating toxins, and invading inflammatory cells responding to the site. Looking at step 5 of the chart, these ROS drive the process of lipid peroxidation is now being dismantled from the inside out by its own unchecked secondary messengers and free radicals. In step 6, widespread microscopic cell death translates directly into macroscopic structural failure of the entire nephron. Dead and swollen cells tear away from their foundation and tumble directly into the narrow lumen of the tubule. This cellular debris aggregates, combining with specialized proteins to form thick, solid structures known as casts. This diagram shows how these casts physically obstruct the flow of the tubule, creating a dangerous backup of intratubular pressure. Systemic metabolic acidosis, a condition where the blood becomes overly acidic, further poisons the cellular environment during this phase of structural failure. The condition has escalated from a localized biochemical deficit to a mechanical plumbing failure. The tubule is physically blocked, and filtration comes to a halt. Step 7 brings the body's immune system into the fold. The accumulation of cellular debris and ROS triggers a massive, localized inflammatory response. Inflammatory cells release specific chemical messengers called cytokines, notably IL-1, IL-6, and TNF-alpha, which are seen here recruiting leukocytes to the injury site. These recruited leukocytes cause endothelial activation within the blood vessels, which paradoxically drives further local ischemia and worsens the tubular injury. In step 8, The systemic body senses below kidney flow and attempts to compensate by activating the ROS pathway. The renin-angiotensin-aldosterone system, or ROS, is a hormone network the body uses to elevate blood pressure and preserve blood volume. Hormones like angiotensin and aldosterone alter the afferent and efferent vascular tone to try and force filtration pressure back up. Antidiuretic hormone, or ADH, is also released. ADH instructs the kidneys to hold on to water, forcing increased water reabsorption. This compensatory effort has a fatal flaw. The prolonged vasoconstriction from these pathways further starves the already ischemic kidney of blood. The body's own survival mechanisms, inflammation and vasoconstriction, trap the kidney in a devastating feedback loop of worsening ischemia. Step 9 is where the microscopic cascade becomes a macroscopic, measurable clinical syndrome, organ failure. The physical blockage by casts and the severe loss of perfusion directly cause a sharp reduction in the glomerular filtration rate. Glomerular filtration rate, or GFR, is the calculation of how much blood passes through the tiny filters in the kidneys each minute. This reduced GFR inevitably leads to a rising accumulation of serum creatinine in the blood. Creatinine is a normal waste product of muscle breakdown that healthy kidneys constantly filter out. Patients experience severe volume overload, often manifesting as oliguria. Oliguria is a massive and dangerous drop in daily urine output. The destroyed transport machinery causes severe electrolyte derangements, including acidosis and dangerous hyperkalemia. Hyperkalemia is an abnormally high concentration of potassium in the blood, which can trigger lethal cardiac arrhythmias. The patient's systemic symptoms are a predictable mirror of the specific transport pumps and structural elements that failed at the cellular level. Finally, Step 10 dictates the cell's fate. The ultimate outcome for the individual tubular cell depends entirely on the severity of the initial ischemic insult. Severely damaged cells will undergo irreversible apoptosis or complete necrosis. Apoptosis is controlled, programmed cell death, while necrosis is the unregulated, messy destruction of the cell. However, a full recovery is still possible. Surviving epithelial cells can rapidly divide and spread out to replace the dead tissue. This chart highlights a critical caveat. This partial regeneration can only occur if the underlying structural basement membrane remained preserved during the attack. Acute tubular injury is a strict race against time. Halting the cascade before the basement membrane degrades is the singular difference between temporary failure and permanent organ loss.